Good morning, student. Myself, Dr. Chinsani from Department of Mathematics, Devgiri Institute of Engineering and Memory Studies, Aurangabad. Now, I am teaching to you Engineering Mathematics 3. So, first of all, I will share to you the screen of me. So, this is our first lecture. So, in this lecture, we see the definition of Laplace transform, introduction to Laplace transform, introduction to Laplace transform. The learning objective of this lecture, by the end of this lecture, student will able to know about the definition of Laplace transform as well as it can find Laplace transform by using definition of Laplace transform. Okay, so the first we see the introduction of Laplace transform. The Laplace transform invented by the French mathematician Laplace, whose duration is 1749 to 1827, and it systematically developed by British physician Heaviside, whose duration is 1850 to 1925, and then it was first of all applied to the problem of electrical engineering. Basically, Laplace transform will convert one function in some domain into the function in another domain without changing the value of the function. That is, the Laplace transform operator changes function in one variable, usually it will be denoted by t, to a function of another variable which will be denoted by s. The main use of Laplace transform is to solve initial value problem for linear as well as linear ordinary or linear partial differential equation. Now, the Laplace transform can reduce ordinary differential equation to algebraic equation and partial differential equation to ordinary differential equation. And we know very well that transformed equations are very easy to solve. So, also Laplace transform is widely used by electronic engineers to quick solve differential equation occurring in analysis of electronic circuit. And the Laplace transform used to solving digital signal processing problem also. So here we see some practical uses of Laplace transform. So first one is practical uses. First one is sending signal or any two-way communication medium, study of control system, analysis of heating, ventilation and air conditioning, simplifying calculation in system modeling, analysis of linear invariant system, and traffic engineering is the application of Laplace transform to the quantification of the speed control in modeling of road bumps with hollow rectangular space. These are the some practical uses of the Laplace transform. Now here we see one video of application of Laplace transform in control system. So
Applications of Laplace transform in control systems. At the end of this lesson, you will be able to define the Laplace transform, explain the use of Laplace transform in a control system, and discuss the applications of Laplace transform in a control system. Introduction to Laplace transform in control systems. Robots. We see them everywhere. They assist humans in performing dangerous and repetitive tasks. And they are currently being used in fields like manufacturing industry, healthcare, military, and yes, the list is endless. In the manufacturing industry, tasks such as welding, painting, and assembly are carried out by robotic arms with high precision. In order to control the speed and position of the robotic arm, mathematical modeling of the robotic arm and a suitable controller is needed. Then, the transfer functions are derived for mathematical modeling of the system through which the stability of the system can be evaluated prior to fabrication. So, a transfer function is a mathematical expression which relates the input and output variables by using Laplace transform. Laplace transform is an integral transform method that converts a function small f of t in the time domain into function in the Laplace domain capital F of s. And it is particularly useful in solving linear ordinary differential equations. It is a very powerful mathematical tool applied in various areas of engineering, especially in control systems. Come on, in this topic, let us discuss more about the use of Laplace transform in control systems. Laplace transform in control systems. A control system is an interconnection of components forming a system configuration which provides a desired system response. In simple terms, a control system takes in data as input, processes the data, and then sends out the desired output. Here, the components in control systems are classified as electrical, mechanical, hydraulic, thermal, and so on. All these components can be described by mathematical modeling such as integral differential equations of various orders, while the output of control systems for any input can be obtained by solving such integral differential equations. For example, obtain the expression for y of t which satisfies the differential equation shown on the screen, and neglect the initial conditions. Mathematically, it is very difficult to solve such equations in time domain. Hence, to solve such equations, the Laplace transform converts them into simple algebraic equations. Then all the complicated computations can be easily performed in S domain as the equations to be handled are algebraic in nature. Such transformed equations are known as equations in frequency domain. Then, by eliminating unwanted variables, the required variable in S domain can be obtained. By using the technique of Laplace inverse, time domain function for the required variable can be obtained. This is how Laplace transform is used in control systems, which makes the computation easy and produces the desired manipulations in the result. Let us see some more applications of Laplace transform in control systems. The first one is the automobile speed controller like automatic cruise control. Automatic cruise control is an excellent example of a control system found in many modern vehicles. The purpose of the cruise control system is to maintain a constant vehicle speed despite external disturbances, such as changes in wind or road grade. This is accomplished by measuring the vehicle speed, comparing it to the desired or reference speed, and automatically adjusting the throttle according to a control law. In order to control the vehicle speed compared to the reference speed, Laplace transform of modeling equations is needed. And the second one is missile launcher. In a missile launcher, the Laplace transform is needed to find out the required turn to track down the enemy aircraft at any time. Now, hope you understood how Laplace transform is used in a control system and its applications. Conclusion. Through this topic, we saw the applications of Laplace transform in control systems. Besides these, Laplace transform is a very effective tool to simplify very complex problems in the areas of stability and control. It goes without saying that Laplace transform is put to tremendous use in the engineering field. Summary. This brings us to the end of the lesson. In this lesson, we have learnt about the Laplace transform. It is an integral transform method that converts a function, small f of t, in the time domain into function in the Laplace domain capital F of s, and particularly useful in solving linear ordinary differential equations. Then, the use of Laplace transform in control systems, and the applications of Laplace transform in control systems.
Now we see this beautiful video in which we see the application of Laplace transform in robotics, in missile launcher. Okay, and it will be useful in to control the speed of vehicle also. Okay, so now we see the first definition of Laplace transform. So first of all, let f of t be a function of t defined for all t greater than equal to 0. Then the Laplace transform of f of t denoted by L of f of t, or in some it will be written as f small f bar of s or capital F of s, and is defined as, so L of f of t is equal to f bar of s or f capital F of s is equal to integration from 0 to infinity e raised to minus st f of t dt. So this is the definition of Laplace transform, basic definition of Laplace transform. Now this f of t is a domain of t on which we apply the operator L, then we have the value which is in terms of s, that is in a domain of s, that is domain of frequency. After finding or evaluating this integration from 0 to infinity, we get in terms of s. It means that this is said to be the f of s. So provided this integral exists, means we say this L of f of t means Laplace transform of f of t if and only if integration 0 to infinity e raised to minus st f of t dt will exist, and where this s is the parameter which may be real or complex, which may be real or complex. So see, this is the basic definition of Laplace transform, or also fundamental definition of Laplace transform. The whole chapter Laplace transform is depends on this definition. Okay, so after that we see the sufficient condition for the existence of Laplace transform. It means that the Laplace transform exists if and only if the Laplace transform of f of function f of t exists when the following sufficient conditions are satisfied. F of t is a piecewise continuous function. And what is meant by f of t is piecewise continuous function? That is, f of t is a continuous in every sub-interval, and f of t has finite limit at the end point of each sub-interval. Then that function is said to be piecewise continuous. This is the first condition, and the second condition is f of t is exponential, is of exponential order of alpha. That is, what is meant by exponential order of alpha? There exists a capital M and alpha such that mod of f of x less or equal to capital M e raised to alpha t for all t greater than equal to 0. In other words, the quantity e raised to minus alpha t f of t, when we take the limit t tends to infinity, this quantity must be finite. Then and then only we can find the Laplace transform of that function. It means that we can find Laplace transform of that function. Those functions satisfy these two conditions. First one is f of t is piecewise continuous. and second one is exponential order of alpha. So sorry, this is the existence condition of Laplace transform. Now we see some example on definition of Laplace transform. So the example first, find the Laplace transform of the following by the definition. First example is this: f of t is equal to 3 or 0. The function f of t having value 3 when it lies between, see, suppose this is 0, this is t, this at end it is infinity, this is your f of t, right? In between 0 to, suppose here is 5, in between 0 to 5 the value is 3, right? And up to t greater than 5 means, what is by t greater than 5 is nothing but is equivalent to said to be t lies between 5 to infinity, means up to 5 to infinity the value is 0. And remember the Laplace transform defined from 0 to infinity, right? So solution, first of all we know that the definition of Laplace transform f of t L of f of t is equal to integration 0 to infinity e raised to minus st f of t dt. Firstly, what we do? We split this 0 to infinity into 5 and 5 to infinity, like or according to the condition given to you. That is 0 to 5 e raised to minus st f of t dt. But when your function lies between 0 to 5, the value of function is 3. When your t greater than 5 means 5 to infinity, the value of f of t is 0. Due to that reason we write this. But this 0 into something is 0 and the integration of 0 is 0. It means that this total term equal to 0, and this 3 is a constant, take outside. So and use integration e raised to ax dx is equal to 1 by a e raised to ax. So using that formula, we have these three constants. The integration of e raised to minus st is e raised to minus st divided by minus s from 0 to infinity, and the integration of second term is 0. Now we put this upper limit minus lower limit, means this small t replaced by 5. So e raised to minus 5s divided by minus s, this upper limit, then we take minus lower limit is 0, so e raised to 0 is a 1, so 1 upon minus, yes, this minus become plus, this 1 this minus, then this, yeah, minus is common, so we have 3 by s, 1 minus e raised to minus 5s, and this is the Laplace transform of the given function 1. Now we see the next example. Now see, second example, f of t is equal to cos t or sin t. The f of t having value cos t when it lies between 0 to pi, and the f of t having value sin t when it lies between t greater than pi, it means from pi to infinity. Again similarly see here, your Laplace transform defined from 0 to infinity, but this interval can be split into 0 to pi, and in 0 to pi the value of function is this, and in pi to greater than 0 is the sine, means this is cos t, this is sin t, right, up to infinity, this is t, this is your f of t. So again same, we know that the definition of Laplace transform is, we know that L of f of t is equal to integration 0 to infinity e raised to minus st f of t dt. But see, integration that will be equal to, we split this 0 to infinity as 0 to pi and pi to infinity according to given condition to you, right? So, but when your function lies between 0 to pi, the value of function is cos t. When function lies between pi to infinity, the value of function is sin t. And now our aim is only to evaluate this integration, these two, but these two integration we can't evaluate directly. So for which we want to require these two formulae. First one is integration of e raised to x sin bx dx is equal to e raised to at, e raised to at sin bt dt is equal to e raised to at a square plus b square into a sin bt minus b cos bt. So using this we find this, and in this formula put a is equal to minus s, b is equal to 1, and so similarly this formula used to evaluate this. Here also a is equal to minus s and b is equal to 1, and put these two value here, and using these two formulae we obtain the integration, that is this two, right? Now here put upper limit, this 1 upon s square plus 1, 1 upon s square plus 1 take common, and put upper limit minus lower limit. When you put upper limit, so e raised to minus pi s, yes cos pi. When we put upper limit sin pi, so it is sin pi is 0 because sin pi equal to 0. Also minus 0. When we put lower limit 0, e raised to 0 1 into minus s cos 0 minus sin 0, and that sin 0 putting the value 0. So plus this is the up to this. Now plus when we put t equal to infinity, so we get e raised to minus infinity, right? E raised to minus infinity means what? 1 by e raised to infinity means what? 1 upon infinity. But it is 1 upon, what is by infinity? Infinity means 1 by 0. So this 0 will be reversed, that is 0 by 1, and that is equal to 0. Now from this lecture, remember that e raised to minus infinity is always 0. Remember this thing. We use this many times. So now remember e raised to minus infinity is 0. So when we put upper limit, so e raised to minus infinity 0. 0 upon something 0. 0 into something 0 means we get 0. Minus when we put upper limit, so e raised to minus pi s, cos sin pi is 0 into minus s 0 minus cos pi. And remember cos pi is minus 1, cos pi having value minus 1 and cos 0 having value 1, means it is minus 1 into minus, it is plus yes. This cos 0 is 1 into minus, minus yes. This cos pi is again minus 1, this plus, and total become 1 upon s square plus 1 e raised to minus pi s in bracket s minus 1 minus 1. So this is the Laplace transform of the given function f of t. So this about the example. So now we see the next example. Now see this split into three times. So again same. We find the, this is our third example. Now here we find the Laplace transform of this. So see how, so first of all it is 0, it is your f of t, it is your t, so lastly infinity, suppose it is half, it is 1, means in 0 to half the value is t, in half to 1 the value is t minus 1, and from 1 greater than 1 the value is 0, means again we know that the Laplace transform of L of f of t is equal to integration 0 to infinity e raised to minus s t f of t dt. And what will be equal to that? So that will be, we split this 0 to infinity according to given condition. How it will be equal to 0 integration from 0 to half plus integration from half to 1 plus integration from 1 to infinity. But when your t lies between 0 to half, the value of f of t is t. When your function lies between up to 1, the value is t minus 1, and when your t greater than t is 1, the value of function is 0. Now see, this 0 into something 0, and the integration of 0 is 0, so we get the 0, means the third integration is 0. So we want to find only these two integration, right? So, and using this formula, integration u v dx is equal to u integration v dx minus u into integration of du by dx integration of v dx into dx, or we also use this formula, integration u v dx is equal to u v1 minus u dash v2 plus u double dash v3 minus and so on. What is by v1, v2, v3? v1 is nothing but integration of v1. v2 is nothing but integration of v1. v3 is nothing but integration of v2. Similarly, u dash is derivative of u double dash is derivative of u dash, and so on. So using this formula, u is t and it is vy, using also LIATE rule. So which function we take the first u as? So using light rule, L logarithmic, inverse, algebraic, trigonometric and exponential, means logarithmic function है तो उसको पहले लेना है, inverse को बाद में. So this is the order to take the first function u. So here t is a algebraic function, that is this is u, and e raised to something is a exponential function, that is v, and u into v. So we get this limit from 0 to half. Similarly, t minus 1 is u and this is the v. So again same formula. So we get this. Now put upper limit minus lower limit, we get this. After calculate, after putting upper limit minus lower limit, we get this quantity, and after calculating all these things, we have the solution. That is, in last we get 1 upon s square minus 1 upon, sorry, e raised to minus s upon s square minus e raised to minus s by 2 divided by s. So this is about the example on definition of Laplace transform. Now student, some exercise to you here, and you can solve this, and these are the very easy. So first one is f of t is equal to t or 6 for the interval 0 less than t less than 3 and for t greater than 3. Similarly, second example, f of t is equal to t square of 0 for this 0 to 1 and t greater than 1. Third and fourth example is this one, and the last one is this. So this is about the today's lecture. So this is our first lecture. So in next lecture we see the sum Laplace transform of some elementary function. So today we stop here. So thank you all.